So good afternoon, dear students. I think I am quite audible.
Yes, sir.
Okay, so today what we are going to talk about, this is a little continuation of our last class where we were talking about the photometry. We already have talked about the different types of photometry. We have already mentioned how the luminous flux can be measured in a two-way. One, we have the direct way, that is using zonal lumen method. Another is a substitution way, which is very popular throughout the globe, called integrating sphere-based methods. We have seen the merits and demerits of both the type of measurements. Integrating sphere-based measurement, the only drawback what we have every time in which we should have a calibrated lamp, which we call luminous flux transfer standard lamp. So it may possible that you don't have this one. But in the other way, if you are going by the direct method or zonal lumen method, where you are dividing the entire space with the small zones, so that type of measurement have only one problem. You should have a very good calibrated sensor. That is essential for all type of measurements. So that's why this kind of equipment, actually, this kind of methodology actually looking for measurement of luminous intensity in different angles. Already we have talked about the spherical polar coordinate system. We have already talked about the generic C gamma, B beta, A alpha type coordinate systems. We know that for indoor cases, we do go by the C gamma. Street lighting luminaire applications, we also go by the C gamma. Flood lighting cases, we do refer B beta coordinate system. So those type of coordinate systems are very much used. In our luminaire photometric classes, we already have seen how that coordinate systems are becoming relevant. So in this way, no matter what type of luminaires we are dealing with, based on the application, indoor or outdoor, basically we are going to measure the intensity value in the two different angles. So that's why the 2D matrix I was talking about, that will be the input for all of you. Whoever is going to calculate the luminous flux using zonal lumen method. Now at each zone, we can calculate, so that part I will show you later on. That is a very simple method which can be adopted. We can divide the different gamma angle with the different zones. So at different zones, we will be going to measure the intensity. And mid-zone intensity of that particular zone will be considered. So that point I will be going to talk later on. Now, but it is very important that in this case also we should have the 2D matrix, which comprises of the two angles and one the intensity value. So that's why from the very first day I have taken your utilization illumination classes, I have mentioned that luminous intensity is the most necessary parameter. Luminous flux is a fundamental, thus luminous intensity is the most necessary parameter. So that means here, once we are dealing with the luminous intensity, we need to specify the point in a three-dimensional plane. So that's why we have the spherical polar coordinate system. Another thing is that the three type of coordinate systems already we have talked much earlier and several times. So the C gamma and B beta. Today we will see how that instrument actually works. So this is a B beta type of instrument. This is housed in our laboratory. This is a very old one and mostly manual in nature. In case of this type of goniometer, we call it type B goniometer. So if you can recall back our previous lecture, I have mentioned the type B goniometer, for which are used to measure the luminous intensity for floodlight luminaires. Type C goniometers, which are used for sake of measurement for case of all indoor and street lighting luminaires. So in this type B goniometer is a very old one, and here you will see the bright illuminated portion is basically a source. So here you will see that how the source is, but this is how the luminaire is mounted. Now using this arrangement, we can rotate the luminaire in left and right. So you'll be able to see here the left and right, and also so there is a scale. So here you will be able to see a circular scale which will take care of at which angle you are rotating in the left and right. And here this portion, which is magnified over here, rotating this one, we are vertically rotating the luminaire in up and down. So that's how my intention is to get the two angles, the horizontal angle and the vertical angle. So that's how we are generating the set of horizontal angles in left and right. And with the vertical movements, we are achieving the different vertical angles with up and down. And my sensor is placed far away, and we are not going to move my sensor anymore. So this is fixed at a point, duly aligned such a way the center, photometric center of my source should align with the sensor. So far away. Can anybody tell me what should be the distance at where I can put my sensor? So this should be preferably such a way, it should be large enough, such a way my extended source, this luminaire, will treat to be a point source. So that is why my sensor should be placed far away from the source. So that is a very, very important criteria you should follow. And now I will be fixing up the sensor. I will rotate my source in left and right. So we can think see 0, 5, 10 in this way, left and right, and also in the up and down, so to get the different set of values. So that is actually what we are always looking for. We should ensure that movement, that is a C gamma, B beta, no matter, this is a B beta type of coordinate system, already I have told you, but again I want to tell you one thing, that it doesn't mean that always we will be going by B beta. Say I have a flat light luminaire, then I can comfortably measure using the type B goniometer. But unfortunately, if I don't have a goniometer which can measure C gamma system, and somebody has given me a, say, an indoor luminaire or a street light luminaire, what should I do? Is it I'll not be able to measure? Yeah, I can do this, because here only a 90-degree shift is required in the vertical plane. So if we can recall back the coordinate system earlier in our last few classes, so there you will see, so here C gamma and B beta, the only change is that there is a 90-degree shifting of the luminaire in the vertical plane. So that's how here you have to calculate mathematically the all angles, how they are getting shifted. I'll be measuring the data in the B beta form, and finally by angle conversion, by coordinate shifting, I'll be changing all the C gamma to B beta, all the B beta to C gamma. So that mathematical calculation we need to do, but it is quite possible. And let me share one thing with you, that we used to do that very frequently, because we have another type C goniometer also, but somehow this was not working perfectly. So that's why we used to do this all sets of measurement for any research work, no matter whether C gamma or B beta mode. We used to measure using this one and used to convert mathematically. So that is quite feasible. So, and the name goniometer, already we have mentioned that gonio means measurement of angle and photometer means measurement of light. So this is an integrated equipment. This is a new equipment, a mirror gonio distribution photometer we used to call, that is used as type C goniometer. Before I talk about this one, in very nutshell, I am telling you that in our laboratory, we have a new version of goniometer 2, which is a fully automatic and LED based. Because for the LED, previous class I have mentioned earlier that the interval of each angle should be as small as possible. We already have talked about the 5-plane photometry, C0, 22.5, 45, 67.5, 90. But instead of that, we can go for, you're supposed to go for 1 degree interval of C. So that's why you can imagine what should be the volume of the matrix what we are generating by this. So that is why this large goniometer for the LEDs should be mostly automatic in nature. That's a new one we bought a couple of years back now, which is very much functioning. But the issue is that here you don't have that much of manual intervention. So it will automatically do. It's a robotic sort of thing. So there is an arm, so you need to just use a laptop, and there is a dedicated program. You set what are the ranges you want. It will automatically take the data. It will rotate, the robotic arm will rotate the entire luminaire in up and down and left and right, and accordingly it will record all the data instantly. So that's why it's a fully functioning, and this is a fully automatic. But Still, we do refer this one because that is a very classical one and very much manual in nature. So that's why you will know how to operate with this type of goniometers. But again, this is a type B. Now come back to our type C goniometer. So this is what we call mirror gonio-photometer. So this is actually for that case, one experiment is there for your senior, but unfortunately we can't do it here. So I can share that particular slides with you such a way we'll be able to know how we can do our measurement using the mirror distribution photometer. This all the coordinate system stuff we already have talked about. That is a mirror distribution photometer. The concept is very simple. Forget about the mirror. So here in type B meter, what we have seen, my source is rotating in a left, right, that means in a horizontal plane as well as in the vertical plane. My sensor is fixed. But for this type of meters, for this type of goniometers, type C goniometers, my source is rotating at the horizontal angle and my sensor is rotating at the vertical angle. So that's how we are going to get the sphere, isn't it? We are supposed to get a sphere. But if I rotate, if I fix up my source at a particular angle, say 0 degree, and here is my sensor mounted at the bottommost portion of the conical shaped baffle. Why conical shaped baffle? Why this arrangement? We will come to that point. But right now I can tell you here, with this bottommost portion of that, we have the sensor mounted. And we are allowing the sensor to be rotated with this axis. So if I rotate 360 degree, what am I going to get? Anyone? If I rotate my sensor, which is mounted at the bottommost portion of this one, if you follow my cursor. So if I rotate it for 360 degree in the vertical plane, what we are going to get? We are going to get a circle, isn't it?
Yes, sir.
But we are supposed to get a sphere. What can I do then? Can you suggest anything?
In both planes, for horizontal and vertical planes.
Right. So that means, but this will be really a cumbersome job if we are rotating the sensor also in the horizontal plane. So that's why what we are doing, we are allowing the sensor to be rotated in the vertical plane, and let's rotate my source with respect to its axis in the horizontal plane. So that's how I will fix up the source at 0 degree. Let us rotate the sensor from 0 to 360. Then change the C degree to 90 degree or any desired angle. Again, rotate the sensor to 0 to 360 degree. So that's how we can reach to the sphere, because that's how our spherical polar coordinate system works. Okay, so that is the idea of this case. So, but in this type C meter, we are rotating my source in horizontal plane to get the different C angle, because we already have talked the C angle is my horizontal angle. It's a vertical plane, but it's a horizontal angle actually. So how we can achieve the different horizontal angle? By rotating the C. And if we rotate the sensor in the vertical plane, that's a different series of gamma angle. So that's how we are finally recording all the data. If we start recording the data manually, automatically, using any data acquisition system directly from the sensor, if we can just record it somewhere, that will give us a very, very comprehensive outcome. So that's how C angle, gamma angle, and the intensity we can get. So C angle means the source, horizontal angle of the source, and gamma angle is the sensor here. Now, this is very simple, I think. Do you have any doubt with this? If not so, then let us see. There is one very specific criteria. The fundamental arrangement of type C goniometer is very much there with your screen. This is the gonio-photometer, the mirror gonio-photometer we have in our laboratory. So here you will be able to see. This is my source or the luminaire. Here you can see the baffle. Can you see the baffle? Can you see the baffle?
Yes, sir.
So at the bottommost part of the baffle, there the sensor is mounted. Can you follow my cursor? So now we will rotate my entire sensor with centering the source. Okay, so that's how we will follow that measurement. Now here you will see the light emitting portion is in downward direction. So that's why we need to ensure that no light will reach to the upward or somewhere else. Now this is the setup, but the question is that why we need to have a mirror. So the idea is very simple. I'll rotate my luminaire with its axis from 0 to different angle with the desired interval. And here we have the sensor mounted like that. Now the question is that I'll rotate my sensor with the vertical plane with a different angle, desired angle, maybe 5 degree or 10 degree interval. The thing is that what is the role of mirror? The idea is that here my entire spherical polar coordinate system will only be applicable. I think from the very first class I have mentioned, it should be a point source. If you have an extended source, you will never be able to develop your sphere with a particular radius r. So that's why here my job is to make the point source realization. So it's an extended source which will be considered to be a point source. So how can I do this extended source to be considered like a point source? So that's why a point source realization will be a vital parameter here. The only option is that here, if you can maintain a sufficient distance between source and sensor, then we can maintain the extended source to be a point source. So that's how here physically the distance between source and sensor is required to be maintained sufficiently high. A radius should be higher, isn't it? Last type B meter I was telling also it should be far away. But the problem is that here in our laboratory premises we don't have that much space because you can't maintain this distance very high. So that's why we are using a mirror. The concept is that light will come from the source to the mirror and then it will reflect to the sensor. So my sensor is mounted at the bottommost portion of the baffle just to ensure that no direct light should reach from the luminaire to the sensor. So that's why this is a black baffle. It's not a completely hollow baffle. If you see, there are some concentric notches. At the bottommost part, the sensor is mounted just to ensure that no direct light should reach to the sensor. If it happens so, the point source realization will be invalid because the distance between the sensor and source is not sufficiently large. That's why we are forcing the light to go to the mirror and then reflect back. That means we are introducing a term called optical distance. So the optical path, whatever light has traveled. So that's why my optical distance should be sufficiently large enough to ensure a point source realization. The idea is very simple. If the distance between the source or luminaire and the mirror is small d, can anybody tell me at which distance back of the mirror my image will be formed? At which distance my image will be formed? My image will be formed with the small distance d, small d, whatever, at the back of the mirror. Now that image, whatever, the image of the source will appear to be a virtual source to my sensor. So if the distance between mirror and the sensor is capital D, can anybody tell me then what is the optical distance between the source and the sensor? Anyone? Are you getting my point? So this is another view actually. So here you'll be able to see if this distance is much less. So I am forcing that no light should reach from the source to the sensor directly. I am forcing the light to go to the mirror and then reflect back. So that's why if this distance, the distance between source and mirror is small d, so the image will be formed at the small d distance at the back of the mirror. So now that image will appear to be a source like my sensor. So now the distance between this image and the sensor will be small d plus the capital D. Capital D is the distance between the source and meter. So that's how. Here another view. Here you will see the control panel. We have to change the angle of the luminaire. This is a completely microcontroller controlled. And also we ensure that there are the motors. So here you can see the gear assembly, the belt pulley, and here the motor which will rotate the mirror and the sensor as an axis. So that's how we can ensure a point source realization. So if somebody asks you that why we need to have a point mirror, just to ensure that. But the baffle is required because if mistakenly any direct light reaches to my sensor will not capable to differentiate whether it is a direct light or indirect light. So if it is a direct light, so my point source realization will be completely invalid. My measurement will be completely erroneous. So that is this is a new version. You will happy to know that we bought one that is also a couple of years back. Goniophotometers we bought. The cost was something around 60 lakhs, I think. So this is a fully automatic goniophotometer, completely robotic one. So once the pandemic will be over, I will take all of you to our laboratory to show this, because this is an asset you should know that our department and we all have. That is a polar graph. I think this semester already I have introduced the polar experiment with all of you, right? So the polar graph you have already plotted. So here as C gamma, we can plot the polar in the same way as in the other cases we can do. So that is the finally the result will be different C angle, different gamma angle, and the intensity. So if I have one, I can check just 1 minute. Just I can show you how it's actually look like the report. Just how the data will look like, so then you can realize the significance of that measurement of intensity. So that is one of my previous student of master degree who did that experiment. So just see the table. Here we first fix the horizontal angle of the luminaire C 0 degree, gamma 0, 5, 10 we have changed, and we have recorded the intensity value. Okay, so can anybody tell me I am measuring the lux, I am supposed to get the intensity. How can I do that? Anyone?
So distance will be 1 meter.
Yeah, here distance is not 1 meter. Here it should be distance square, but here I have told you the obstacle distance. So here the distance should be distance between the source and the mirror plus mirror to the sensor. So that distance is sufficiently high. So in your experiment, in our photometric tanks, we have used 1 meter, but here instead of 1 meter, we have used 5.3 meter, 31 meter, which is a measured one. So that's why the measured illuminance value will be multiplied with d square. So that is what inverse square law we already have talked earlier. The inverse square law. Using that, so at each C angle, you can see C different gamma and the intensity. C 22.5 different gamma in the same gamma and the intensity. So that's how you will see that C 45 degree, C 67.5 degree, C 90 degree, and gamma versus intensity, they are actually plotted. So finally, I asked him to plot that. So that's how in a different plane he plotted the intensity value. That is just for your reference. If you are interested, I can share that document with all of you. So that is actually how a standard goniophotometer basically works. And that's how we can measure the luminous intensity value for different planes. So here, the modern goniophotometers are like fully automatic one, as I was telling you, LED photometers, because here C and gamma, both interval has to be made as small as possible. So that's why here it should be very much fine resolution. So here photometric measurements also compiles with the 4 characteristics which are very essential for any measurement. The number 1, accuracy. Number 2, precision. Number 3, resolution. Number 4, sensitivity. So that's while we are talking about the any measuring instrument, I think in your second year measurement classes you already have gone through. That is the 4 parameters, characteristics parameters are used to quantify, characterize any measuring instrument. So here also the photometric instruments are coming under that. The accuracy, with respect to the standard, how accurately it giving the value. The precision, that is the repeatability of the accuracy. We have sensitivity, that means if there is a small change in your input, whether your output varies at all or not. And lastly, what we all know, that is what we call resolution, the least count. So that is the 4 parameters are equal, applicable for all the photometers here. Okay, so with this, we can conclude the photometry. The zonal lumen part I'll be sharing with you later on, but today let us start talking about the design, introduction to the lighting design in very nutshell. Any doubts so far from the photometry classes? Any doubt?
No, sir.
By the way, just I want to know one thing, that how long your this semester will continue? That means theoretical classes will be possible up to next week or next to next week.
Sir, we have no idea about that.
Officially, 15th is the result.
Yes, sir, 15th May, sir, I think.
15th May. Okay, so that means we can get at least 3 more classes, because the communication classes I have to also take. That I need a sort of interaction from you. Okay, introduction to the interior lighting design. Why I am talking about the interior lighting design? So now we already have gone through the different lamp, luminaires, photometry, and now we are approaching to the lighting design. What does it mean? Actually, this is a very common thing. People used to think that put the light here and there and you will be getting the effect. So that's not the lighting design. So I have to, lighting design starts with the selection of light source. So just listen that part carefully, because those are the standard steps which we generally follow. In a generalized mode, people used to think lighting design means put the light here and there and that's your design will be done. No, it's absolutely a wrong concept. Number one. Number two, sometimes we'll see there are some standard lighting design simulators. So simulation softwares are available. We can name something like Dialux. Once in your second year or 4th year, once you will come, some of those who will take illumination as elective, to them we will introduce that lighting design software like Dialux. So this is a German software. And we have many more very interesting lighting softwares which are used to do the simulation. So sometimes we used to think lighting design means using the software, but those are absolutely a wrong concept. So lighting design starts with the selection of lamp. So what type of light source? Even if we are selecting the LED, what should be the luminous efficacy of the LED? What should be the color temperature? What should be the color rendering index? Everything will start with that. Then the wattage, how much wattage I am going to use, and some standard practices we need to follow. That definitely depends with the different conditions. Just for an example, if I have a completely interior place, the design approach will be something different, because if you recall back our previous classes, once we were talking about the coefficient of utilization or utilization factor, then we mentioned also the same thing, that there is a very clear demarcation between the different type of lighting design. The most fundamental is that for indoor cases, we are getting the support from wall, we are getting the support from ceiling, we are getting the support from all the surfaces other than the floor. Floor is always there. But if we are talking about the outdoor applications, though in a real situation we know there are the different structure, architecture, different building facades exist, but in a true sense, while we are going to do a design, we are not going to get any support from neither from the ceiling nor from the walls. We only have the floors or only on the surface, road. So that means that's how once we are doing the indoor lighting design cases, we are having one advantages as well as disadvantage too. The advantage is that we are getting the support from the other surfaces. So that's why right now what I am getting here in my tabletop, this is not the direct component which is coming from the source. This is direct as well as reflected and interreflected components. So what is a sustainable lighting design? Here you will see people are talking about the smart lighting design. We are talking about the human-centric lighting design. I'll be taking a small class on human-centric lighting design soon. So there you will see how the smart systems are getting more and more human-oriented. So today I'm not going in that part, but here it starts with the 6 fundamental blocks we need to follow while we are talking about a sustainable smart lighting design. So you will be quite well aware of the term called sustainable design. Every time today we are talking, we are referring many times. So here mostly energy efficient light source, luminaire and the control gear. So that means here I am selecting a light source which is a very efficient one, but I am not going to select the ballast or the control gear igniter accordingly. You know that in our home today we are becoming alert. I can think about 10 years back, people hardly used to think about electronic ballast or electronic choke instead of the electromagnetic one. Electromagnetic is a cheap, very cheap, whereas electronic ballast cost around almost 3 times than the conventional, but it consumes almost 1/3 amount of power with respect to the standard one. So that's how there are the selection of energy efficient control gear, the luminaire, everything are very much essential. Now here the lighting system with a better vision. So your visual need and the perception is equally required. The perception term I will come back once we will be talking about the human-centric lighting. Energy efficient lighting design. So that all are the part of design. So I have selected my luminaire, I have selected my light source, I have selected my control gear. Now my job is to place them, install them in a very optimized way. Introduction to the lighting control. Just see that once we all are leaving our place, workplace, or maybe the space of concern, so it is expected that the light will automatically get reduced. So that's how the energy efficiency will be ensured. The daylight integration. This is very important today because if you have a sufficient daylight, your automatic light should definitely, the artificial lighting should be automatically tuned with the daylights. And lastly, the light power density and ECBC compliances. So this portion I will be telling you, this is a metric. Bureau of Energy Efficiency, I think you all are well aware of the term BEE, which was during 2002 possibly. Our Ministry of Power, they developed the Bureau of Energy Efficiency, and 2007 BEE has published an ECBC, Energy Conservation Building Code. Initially in 2007 it was published, but every couple of years they used to modify that. Now even if you Google that, you will be able to get the new version of ECBC very much available, possibly 2017 or 19. This is the PDF, entire PDF is available in internet. So this is Energy Conservation Building Code. So what is there in the Energy Conservation Building Code? So once you have done your design, whether your design is very much at par or not, from the energy point of view, there should be a benchmark. The idea is that, so that's why in this ECBC guideline, there is a term called light power density, or abbreviated like LPD. The unit of light power density is watt per meter square. So the idea is that, say, I know what is the area I have, maybe your classroom, you know the area. So that is a meter square, in square meter, how much area you have. That should be calculated from your plan, or maybe you can measure it in real time. Now, you calculate how much of electrical power in watt, unit should be in watt, is installed or consumed for sake of lighting. That find out. So that ratio, watt per meter square, will give you the how much light power density you have consumed. Now, ECBC, they have in their guideline, they have very meticulously mentioned what is the maximum permissible value of watt per meter square, LPD. So that value is given by ECBC. So while being a designer, whatever design you have already performed or you have already designed, So you have to ensure that your design, based upon your design, the LPD value should definitely be based upon the SdC guideline. It should follow the SdC guideline. Okay, so that point we will definitely come. I will give you a space as an assignment. Later on, we can also do that. If you consult our few previous years' question, you will see. Maybe your KCR hall, beloved KCR hall is given to you. Maybe your classroom is given. Maybe the library is given. And the 2-3 options of the luminaire will be given to you. So you are supposed to calculate how many number of luminaires are there by using option 1, option 2, and option 3. And finally, which option is best, that will be given to you. So here, the idea is that efficient light source with a better perception, luminaires with the optics. The luminaire have a very important role. Previously, we have seen the luminaires will redirect the light with your desired reactor, lighting control, payback, and cost. So that is a simple payback problem. So that means how much, say, I have option 1, option 2, option 3. I have designed 3 options. So which one is best if somebody asks me? Just an example of electronic ballast I was telling you. So while I was talking with someone who are very much rigid with the electromagnetic ballast, I used to say, put electronic ballast. Maybe your initial cost will be 3 times. Say 100 rupees is your cost of electromagnetic ballast for 36 watt tube light. And electronic ballast cost is 300 or 250 rupees. So this extra 150 rupees you have paid as your initial investment. But think about, after installing the electronic ballast, every day your electricity bill, which is converted to the monthly electricity bill, saving will be huge one. So you are saving a huge amount of electricity bill using electronic ballast instead of electromagnetic one. So the payback is how fast the extra investment, whatever you have done, you have recovered. So that's what we call payback period. Say for an example, I have told you, you have invested 250 rupees excess by introducing the electronic ballast. And you have seen that in your monthly electricity bill, you are saving 50 rupees. So what will be your payback time? Then your payback time will be 5 months. So that is just simple. So there are some other complicated, complex payback calculation too, but for your case, we will concentrate about a simple payback problem. So this is something we will be talking about. Already I have mentioned the play with the light or engineering. So here the luminaire and its positioning is very also important. At which angle we will be going. For indoor lighting, this is a very standard practice, a general lighting and the localized lighting, or a combination of general and localized lighting. So that's what we want to do with. So whether we will go for localized lighting or general lighting. So mostly the idea is that you have a big room, okay, where your workplace, the offices, think about our HODs. So if it is a big room, the actual workstation is small. There are the places where maybe the visitor will sit, the other meeting will exclude. So that's why I don't need the light all along with a very, very desired value. What I need a specific light, almost an ambient light to be maintained all along. But for my workplace, I need additional light to maintain a desired value. So that is why here it will not be a wise solution to illuminate the entire room with a higher value of light. Okay, so this will be a complete loss. Rather, we'll be using a combination of a localized lighting. Just use the localized lighting as a supplementary lighting along with the general lighting. So here, introduction to interior lighting design using lumen method. So that is a very simple method. Before I want to share with this, so I think here are some examples, as I was saying, that with this we'll conclude the indoor design. Let us discuss about the steps once more. We are going for the equation. The equation is very simple. The step, the first, I am your client. I have shown you just a hypothetical case. I have shown you KCR hall and ask you do a design for the cashier hall. You are a designer. So what you will be looking for? I have given you the AutoCAD layout, the all plan and the side view of the cashier hall. Will it be sufficient? Anyone? Will it be sufficient? Sometime I need to.
Could you repeat once more?
Yeah, my question is that, say, an example of cashier hall I am taking. So I am the Jadavpur University Electrical Department Authority is your client. You are a designer. I ask you that, do you do the design for cashier hall? So what should be the step a designer should follow? The first step, I have provided all the AutoCAD layouts or whatever information I have shared with you. Will it be sufficient? No. So the first question should come from your mind that what is the purpose of this room? What should be the application of this room? Whether it will be just a meeting room, whether it will be a classroom, whether it will be a library, whether it will be a drawing room. So I need to use the specific utility of the room. So based upon that, you have to decide what light level is required to be mentioned. So that's why once you know, this will be used primarily as a classroom, big classroom, and sometimes some meeting can also be held, but or seminar or conferences can be held, but mostly this place will be used like a classroom. So once it has got already decided, so that input I will be going to give you. Otherwise, you will not be able to do the design. If I only provide you the layout or the all plan related information, that will not help you because you should have those data. Once you know, immediately you consult an Indian standard. Just like I have mentioned, the CIE and IIS, they have the standard for interior lighting. In Indian context, we have the standard IS 3646, Part 1 and 2, which was published in 1992. IS 3646. All IS have their specific numbers. So IS 3646, we need to refer. I can share, even I don't know right now whether it is freely downloadable because last year BIS was that means the Authority Bureau of Indian Standard, they were basically giving that one as free. I am a member of that committee who are also developing, modifying this IS 3646, which was published in 1992. Maybe within coming year, we'll be having the new version of IS 3646. But old version, I will be sharing with you that because that is very interesting. What is there in the IS 3646 actually? So if you consult the IS 3646, you will see for all the applications, all the different applications, they have mentioned the recommended illuminance level, average service illuminance level. So average service illuminance level. Classroom, no matter if it is a classroom, be okay. If it is anything, what is the application? So as soon as you know the KCR hall will be treated like a classroom, immediately what you will do, you will open your IS 3646. You see for the classroom whatever recommended light level they have mentioned. They have mentioned 3 different levels: 300 lux, 500 lux, 750 lux average service. 300, 500, 750 average lux of luminance. 300 lux, 500 lux, 750 lux average surface luminance. So what is that 300, 500 and so actually using that 300, 500 and 750 lux average luminance means 300 is a case where the speed and accuracy of the job is very less, number one. Number two, the average user's age is very young. That means you need less light. Young people need less light. And here your room is contributing more light. So the reflection from the room is higher. Maximum one is required. Maximum one is required once my average road surface, average room condition is not supporting. It's dark. So I need more light to reflect. Number one. Number two, here the average age of the user is quite high. 50, 60. They need more lights. And lastly, the condition is that the speed and accuracy of the job is required very high. So that's how the 300, 500, and 750. Because general thumb rule says that if you are not being able to define under which class you are falling, it is preferred that you go for either middle value, the 500 one. Okay, so that is the example. So that is a target illuminance should be known to all of you. Is it clear? That is the target illuminance always known to all of you. Any doubts so far? Any doubts so far?
No, sir.
Okay, sir. So now the next part is that if we are using this one, here we are going to follow this lumen method. So this is a most fundamental and easy method to estimate how many number of luminaires you need for a particular workplace to do a specific design. So that is what we always estimate with the lumen method. So what is there in the lumen method? So in the lumen method, you will see the expression is very much there with you. The expression is basically the dimensional analysis. Can you recall in your 10th level physics, we used to do the dimensional analysis? Both side dimension. Here, if you do the dimensional analysis of the units, you are going to get the illuminances, lumen per meter square, lux. And in the right side, all the parameters, what we have one by one I am explaining. Capital N, the number of luminaires. Small n, numbers of lamp per luminaire. Pi L is basically the luminous flux of a single bare lamp used with a luminaire. And COU, already we have talked earlier, the coefficient of utilization, how much light is getting utilized. And last, a new parameter is a light loss factor. LLF we used to call it. That's what I am going to explain. But apart from that, denominator is length and width. So this is the area of your place, right? So for KCR, how much length you have, how much width, you know from there. So once you know that, so now your measurement will be, or design will be much more accurate. So here, E average, anybody tell me, how do I know for the KCR how much E average is there? So that's why you already have told you that our IS 3646 will tell us how much E average is required. So IS 3646 I will consult, and that IS 3646 will give me the value of E average. Okay. Any doubt so far? Because you have to do your design. So I will be giving you some sort of design to do. Any doubt? Feel free to ask me. If you are becoming so silent, sometimes I am getting scared whether I am disconnected or not. Okay, thank you. So here in this case, we are talking about mostly lumen method. Here, capital E average we are going to get from our standard. So as soon as I know what is the application of the room, E average is known. Now, my function is that to estimate the capital N, the number of luminaires required to illuminate the place, KCR hall. So, light, that is length and width is very much known to me. Length and width is very much known to me. COU of the luminaire is also known. And phi L, you already once you have selected the luminaire, you know the phi L. Phi L. So once the phi L is known, now phi L is the luminous flux per bare lamp. Are you getting my points?
Yes.
Yes, sir.
Possibly I am taking your lunch time, but 5 more minutes is spare. I will completely that portion. So here in this case, the phi L is the luminous flux of a single bare lamp used in the luminaire. COU is the coefficient of utilization. Light loss factor is the depreciation of light because of the different reason. So that is what we call light loss factor. So that light loss factor we need to calculate separately, because that light loss factor will help us to identify how much light has got lost because of the some issues. Some issues like there are the two components which are there associated with the light loss factor. So today I have installed some light. I know after maybe after just 2 years, the value will definitely reduce. Okay, so the value will definitely reduce. So that will be quantified with the light loss factor. So here is an example. Already I have told you that IS 3646. Already I have consulted. I have got a room with a fictitious room of the dimension is given 8 meter into 6 meter into 4 meter. So the coefficient of utilization for that luminaire will be given to you while you are selecting your luminaire, and light loss factor is the two component. One is a recoverable with lots of maintenance. You know, the accumulation of dart, that is a dart depreciation. Your light is getting depreciated because of the accumulation of dart. So that can be recovered with a periodic maintenance. But there are some things which cannot be recovered. So that is what we can call non-recoverable types. Like your lamp's own depreciation, the light will get depreciated. So that is a natural depreciation that cannot be recovered. So it happens so that sort of depreciation we call non-recoverable type. So that's why we have to take a sort of depreciation, just like in any engineering design, we used to take a safety factor of safety with a sub factor. So here in a standard practice, if you have almost in an indoor application, we take it like 0.8. Some odd situation, say you are talking about some cement factory or a process industry, where that value should be something like below 0.5. If you have a very clean room today, like you can make it 0.9. But it is very clear, small and small, your light loss factor you have, your design will be that much over designed. So that means if you are considering your light loss factor at 0.5, that means in a very fast day after your design, you are doing your design almost 2 times over design. So you know the depreciation will occur, and finally after 1 year, maybe after 2 years, your desired value will achieve. So that's why while you are going to select your light loss factor, you have to calculate the light loss factor very accurately. Otherwise, it's a challenging job. The lighting industry, for their own business interests, can manipulate with the light loss factor, but the engineer should be very much specific while calculating the light loss factor. In your case, in your problem, according to your curriculum, we will be providing you the light loss factor values. So that's why you can calculate how much number of luminaires required for the option. So in 2 options, I have said just a hypothetical case. One case is to achieve the same illuminance by option 1, we need 16 number of luminaires, and option 2 we need 23. So we can calculate number of lamps, total power, and finally the energy cost. So that's how you can see my option 1 is much economic from the energy point of view. That's how we can introduce our energy interior design. But again and again, I'm telling you, this lumen-based measurement, lumen method-based calculations are to some extent accurate, but here the all reflected and inter-reflected lights, especially for the interior, are not accurately considered. So that's why sometimes, for sake of better calculation, we need to take the help of the lighting design software. Those are mostly based upon a sort of algorithm called Monte Carlo simulations. So this is Monte Carlo is a very known method which are adapted to take care of an infinite phenomena. So the interreflection is an infinite phenomena. So that's why the Monte Carlo simulation will help us to do that. So that's why the design software, whatever I'm saying, that the dialects or something in their background calculation, that is mostly Visual C++ based, but the algorithm basically deals with the Monte Carlo simulation. So that is the only discrepancy, but in our curriculum, our syllabus, we will concentrate over the this portion only. So with this, let us conclude our today's class. So if you have any query, feel free to ask me. Otherwise, we can conclude our today's discussion here. Anything?
Sir, one question. Why aren't we
Yeah.
considering the height of the room while calculating?
Yes, height. That's a very good question, because height of the room we are definitely considering while we are calculating the COU. If you follow my previous lectures, I have told you for interior lighting design, COU is calculated with the height. So already the height parameter is there. So if you are changing the luminaire position, your COU will change accordingly. So while you are considering, say it's a 5 meter or 10 meter, whatever may be the height, accordingly your COU value will vary. So that's why once we are calculating the illuminance, only the area concerned, the classical definition says that lumen per meter square, so the only area considerations are considered. So that's why the height is definitely taken care while we are considering the COU value of the luminaire. Okay.
Okay, sir.
Anything else? Anyone? So with this, can you conclude today? Okay, next week I'll take the live classes, 2 fundamental classes. One will be on human-centric lighting, another will be on the communication protocol. Okay, thank you. So see you in the next class.
Thank you, sir.
Thank you.